Uh, Good afternoon. I'm Yao-Chuan Tsai from Tohoku University in Japan, and I'm pleased to present my research here today. And my topic is RIE patentry, a patentering technology of zirconia-based mechanical glass for MEMS device fabrication. And this is my outline today. And in the MEMS and the NEMS field, the excellent property of the mechanical glass have already attracted many attention. The mechanical glass is a kind of alloy which have an amorphous structure, and the mechanical property of the mechanical glass is large elastic strain limit and high yield strength. And in this picture we can see this is a micro mirror, and we use the mechanical glass to fabricate the torsion bar of the micro mirror as shown here, and we can see this is mechanical glass. So mechanical glass is a very suitable material for some MEMS device. However, there are few reports about how to patent the mechanical glass. Only like lift-off process and the FIB process. So in this work, the mechanical glass fin by sputter deposition and the RIE patentry are available for further mechanical glass MEMS application. And this page shows the fabrication process. And firstly, the mechanical glass was sputtered on the silicon substrate, and then two kinds of photoresist was used to define the pattern on the mechanical glass surface. And then we use homemade RIE instrument to dry etch the mechanical glass, and finally remove the photoresist. And I will introduce more detail. The mechanical glass, we deposit the mechanical glass by a sputter machine, and the during the sputter condition is shown here, and the target is a zirconia-based alloy, and this zirconia-based alloy is made by the arc melting technique. By the arc melting technique, we can get more uniform distribution of all elements, and we should during the sputter process, the high temperature should be avoided, because if the sputter process temperature exceeds the crystalline temperature of the zirconia-based mechanical glass, the amorphous structure will not be obtained. And for the photoresist lithography pattern, we use two kinds of photoresist to define the pattern on the zirconia-based mechanical glass surface as following RIE etch mask. And different hard baking temperature was applied on the photoresist. And the parameter was shown here. Then a homemade of RIE instrument was used to dry etch the mechanical glass in this work. And the principle of the RIE is remove the elements by iron bombardment. And during the RIE process, the effect can be purely mechanical or chemical. And the mechanical etching means the iron etching, and the chemical etching means the plasma ion reacted with the etching material. And the homemade RIE instrument is shown here, and consists of a vacuum chamber, mixture gas inlet, and circulating cooling system, and RF power, and permanent magnet array. And the excellent property of the mechanical glass is due to its amorphous structure. So it's very important to confirm the amorphous structure of the mechanical glass same thing with the fabricate. So we have two kinds of methods to confirm the amorphous structure. The first one is X-ray diffraction. This picture shows the X-ray diffraction results, and we can see the broad iceberg peak in here is the typical zirconia-based mechanical glass peak, and this peak is originate from the silicon substrate. And the second method to confirm the amorphous structure is the transmission electron microscope, and we can see the diffuse holy ring in here is a typical amorphous structure image. So from both results, we can know the fabricated mechanical glass thin film is amorphous structure. And then we use RIE and for different hot baking condition and different RIE power. And for this test, the working gas and the pressure will make sure with argon 1.5 millitol and C4 Fa 0.5 millitol. And during the RIE dry etching process, the height difference was measurement by the surface provider and the record. And we can see the value of the height difference divide the original photoresist thickness is decreased during the etch time. This means the etching rate on the photoresist is much faster than the zirconia-based mechanical glass. And we get the best result is shown here. The mechanical glass etching rate is around 20 nanometer per minute, and for the etching selectivity is 1 to 3.2 for mechanical glass to photoresist. And for this page, we also try to use different photoresist and different RIE working gas for during the RIE etching. And the photoresist, two kinds of photoresist is shown here, and there are three kinds of the working gas. Is C4Fa, argon, and SF6. And firstly, we can see from the mechanical glass etching rate, we can see for the pure argon is the lowest comparing with other, because the pure argon only have ion etching without chemical etching, and these two have because the fluorine ions have chemical etching in it, so the etching rate will increase. And we see the C4Fa and the pure argon etching in here, and when we increase the C4Fa ratio, the etching rate will increase. This is because the C4Fa have plasma fluorine ions can make chemical etching, but the argon only have mechanical etching. But we can see the etching selectivity also increase because the fluorine carbon compounds from the C4Fa can be increase the photoresist resistance. And when comparing these two parts, and we can see in for the SF6, the mechanical glass etching rate is increased, and for the argon is slow, and for the etching selectivity without decrease. Why? Because the SF6 without fluorine carbon compounds, so he cannot increase the photoresist resistance. So in this result, we can see maybe the working gas we should choose this part for can be etching the mechanical glass first, and can be increase the photoresist resistance. And this page, I show some results of the SEM picture, and we can see the we define some mechanical glass thin film transform from the photoresist and from millimeter scale to the micrometer scale in here. This is metallic glass and this is silicon substrate. And for this, we also need to, after the RIE dry etching, we also need to confirm the amorphous structure. So we use the TEM to confirm the amorphous structure. It is amorphous structure. So this is conclusion. The amorphous structure of zirconia-based metallic glass thin film was successfully deposited by the spark technology and patented by the RIE technology. And the etching rate and the etching selectivity were tested in a different photoresist hard baking condition and different etching eye power. The different working gases during our RIE etching process was also carried out and studied. The basic result is the zirconia-based metallic glass thin film was structured with the 20 nanometer per minute etching rate and 1 to 3.2 for metallic glass to photoresist etching selectivity. And this plasma etching technology realized metallic glass thin painting for advanced MEMS device fabrication in the future. Thanks for your